But anyway, in chapter 13, basically we have different ways that we can represent things. So what we've had in the past is rectangular coordinates. So let me just show we had the X, Y, and Z axis in 3 dimensions. And if I had a point in space, we would call it the XYZ, would be the ordered triplet there. And so basically over X, out X, over Y, and up. Well, that's not a very good dot. I'll just make my dot a little bit bigger. Up Z here. So that's out X, over Y, up Z. So that's out in the first octant there. So that's kind of how we described that before. So what's the, and then we had things, different equations out there like x squared plus y squared plus z squared equals r squared, which was a sphere, stuff like that centered on the origin. So we had different ways of representing things, but remember, these are actually rectangular coordinates. Those are rectangular coordinates in space. So, and my lights go off. And move around here. But anyway, so then what's cylindrical coordinates? Basically what we have is we're going to be able to, I think I could just use the same picture. I'm on page 1070 in the book. But anyway, if I come out from the origin here on the table surface, which is the XY plane, and I say, hey, that's R. We're going to call that R. Let me draw that a little bit bigger. I'm going to redraw it over here in green. But if I come out in the XY plane a certain distance, we call that R. Basically, then I could also look at the angle in between, and they call that theta. So once again, this is the x-axis, y-axis, z-axis here. But I come out to this drop down point. So when this drops down, that's the drop down point there. And this distance R is going to be less than the blue distance, right, that we had before. So this distance right here, whoops, why is that moving around? Is that moving around for you guys or just me? All right, anyway, quit it. But that distance right there from the origin there is bigger. Oh man, that moved around. It is moving around. All right, well, I don't understand what's going on there. So I'm just gonna forget all that. But anyway, this green distance is not as big when we're trying to get to, I'm just gonna put where that blue point was, XYZ. But anyway, this is straight down, right? But we have an angle theta between, once again, positive rotation from the positive x-axis toward the y-axis, just like we do when we're doing sine and cosine, stuff like that. So we started out at the positive x-axis on the unit circle out 1 and then rotated counterclockwise. So the positive y-axis was actually pi over 2 radians or 90 degrees, right? So we have that. So we're going to have angle theta here. In this case, according to my picture, my angle theta is between 0 and pi over 2 radians. And then the question is, how do we get to that height? Well, that height is still given by a height of z, right? So that height of z is still the same height. So this ordered pair, when we look ordered triplet, in cylindrical coordinates is going to be now given by, instead of x, y, z, we're going to be given by out r, that's the distance, angle theta, and then a height of z. So r theta z is how we're going to represent that, and that's going to be the cylindrical coordinates there. Let me erase this if I can, if I remember how. Clear the annotations, and then just look at a couple of things here. Let's see. If I have, we looked at a few examples yesterday, so let's look at that. And go back to a base color here. So let's look at example. If we're in cylindrical coordinates and we have something like r equals a constant. So let's look, I'm going to look at a specific one, r equals 3. Well, if r equals 3, okay, and that's the distance out on the table surface, right? That can be out here, 3 units, but what's unrestricted? Theta and z are unrestricted. In other words, there's no bounds in that. So Z can be up and down as much as it wants. Theta can spin all the way around. And Jordan and I were talking about, like, if you've ever played the game Twister and you got that arrow and you spin it and it spins around, well, that's your theta, but I can go all the way around here. So basically there's the minus y-axis, the minus x-axis, you know, the minus z-axis down these ways here, right? But anyway, so what happens is if R is always going to be the same out here, then what's this look like? I'm going to draw this picture. So like if R is 3, so I'm out 3 this way as well on the y-axis. I'm out toward us 3 units here, 3 units there. This would be minus 3 on the negative z-axis. This would be minus 3 on the minus y-axis. But anyway, what I end up having is a circle. And then, of course, if it's behind, I usually put dashes on the curve. But then I've got it there. Now, that's on the table surface is when z equals 0, right? So z equals 0 is the xy plane. That's the table surface, is kind of how I've been referencing that of late. But, you know, I could go higher than that, too. So if z is 5 up here, I still have the same type of shape, right? What if z is like negative 5? I'm going to use a different color down here. Z is negative 5. I'm going to have, you know, the same shape. And of course, I'm going to use dashed lines behind on that. On top, we can see it all. But anyway, long story short, fill in this graph in. What does that look like? It looks like a cylinder. And so the reason we call r theta z cylindrical coordinates is because r equals a constant is actually what type of cylinder is this? This is a right circular cylinder. This is a right circular cylinder. And so back in chapter 9, so I want you to reference chapter 9 and section 10.6, we talked about these different things, but especially in section 10.6, we were calling them cylindrical, what were we calling them? Anyway, taking a curve and then having a vertical line tracing that curve, and we looked that up. Yeah, they were sheets. It was a surface or a sheet, but then they were calling them it is a surface of revolution, but they were calling it a cylinder. But there's different shapes on those cylinders. So if you go back to section 10.6, you can see that. So then specifically, this is a particular type of cylinder where we have vertical lines. I'm gonna just use orange for the vertical lines. So like I have a generating curve of a circle on the table surface. So that blue circle is a generating line, but then I can take this vertical line and rotate it all the way around into the back and everything else, and ultimately that goes all the way around and makes a empty right circular cylinder, right, that we have. If we were going to rewrite this in terms of rectangular coordinates, I believe we did that back then. We would have, well, what would we have in rectangular coordinate representation? So this is the equation in cylindrical coordinates is r equals 3. But if I wanted rectangular representation of this, so for rectangular coordinates, we would have what? Well, basically we have a circle on the table surface, which is given by x squared plus y squared equals 3 squared, because 3 is the radius, so it's actually equals 9. And then what do we know here? Z is unrestricted. I'm going to put U period R period for unrestricted. anyway, Z is unrestricted here, so it can be as high or as low as it wants, but we're always going to get a circle no matter what the value of Z is, whether it's the purple circle at Z equals 5, or the green circle at Z equals -5, or the blue circle at Z equals 0, right? We're always going to get that. But which one is easier? This is actually an easier formula, R equals 3, when we compare it to the rectangular version of this, which is x squared plus y squared equals 9. Okay, so that's why we have other types of representations. So then when we start taking double and triple integrals, things like that, there's some curves or sheets that have much easier representations in either cylindrical coordinates, which is what we're doing now, or spherical coordinates, which is what we're going to do next in this section. So let's look at another one. What if I have let's see the other constants. I got to get back. I was flipping. I'm in the wrong chapter here. But instead of R equals a constant, what if theta equals a constant? So let's say theta equals, I don't care, 2 pi over 3. So theta equals a constant. Well, if theta equals a constant, once again, here's out x over y and up z. But we start at the x-axis. So if I want to go 2 pi over 3, I'm going to take that x-axis back there. So that's the negative x-axis back here. But anyway, pi is all the way from the positive x-axis to the negative x-axis, right? All the way around, that's pi, or 180 degrees. 2/3 of the way to pi would be where? I'm going to do this in a different color. 2/3 would be right there, right? So here's 1/3 of the way, here's 2/3 of the way. So right here we have theta equals 2 pi over 3. Now, the reality is then what's unrestricted? So we have R is unrestricted, and so is Z. So I can go up from here, and I can go down from there for my Z, right? With that same theta, but then R could be, this is R is the distance out, right? But R is unrestricted too, so it could be farther out than that, or it could be negative as well. R could be negative as well, so it comes this way also. Once again, Z is unrestricted. So ultimately what we get is we end up getting a vertical plane through the origin with an angle of 2 pi over 3. Okay. Now notice, this coming back the other way. I'm going to use a different color here, but coming back this way, this is actually minus pi over 3, because 2 pi over 3 plus pi, if I go all the way around this way, starting at the x-axis, is 5 pi over 3, right? So pi plus 2 pi over 3 is 5 pi over 3. But anyway, so that is basically the graph of this is a vertical plane going through the origin at the angle 2 pi over 3. Once again, a very easy representation when theta is a constant. And then we did one more yesterday for sure. Well, we did a couple more things, but hopefully this is kind of numbing to Jordan's brain here, because we already did it in good review. So if it's easy, that's good. That means we did our job yesterday. So last example, let's just do Z equals a constant. So let's just do Z equals 5. That's what I did before. Well, for Z equals 5, what's that going to look like? What's unrestricted? So we have R and theta are unrestricted. And with that being said, the height is always going to be 5, x, y, z. So right there looks like that's 5. And then, of course, how do I draw that? Basically, I can rotate all the way around because theta is unrestricted. So it's like the twister arrow spinning around, and R can be as big or as little as you want. So the way I can draw this, I can go, kind of along the y-axis there, and then back this way, the x-axis, we're kind of showing this way and going this way and going that way. So what we actually have here is a a vertical, excuse me, a horizontal plane at z equals 5. Pretty easy there. And of course, it goes out forever in all directions, but basically has the height of 5 and can hit any other x, y values, or in our case, r values and theta values, whether the r is positive or negative, and whether theta is positive or negative. But theta, of course, 0 is less than or equal to theta is less than 2 pi, right? So we start at 0, theta goes around and to that. So we do have that restriction. Typically, of course, we could say theta is 3 pi, well, it's 2 pi, and then another pi would be back on the back side of the x-axis. But typically, we're just using theta there. All right, and then hopefully all that makes sense. And you can see there's some very easy graphs based in cylindrical coordinates when we pick one of them to equal a constant. Let's look at a couple other ones real quick here. One was if we had in cylindrical coordinates, whoops, got to get where I can draw again. In cylindrical or rectangular coordinates, when we had let's see, x squared elliptic paraboloid. Let's see if we had, so let's do an example. If I've got x squared plus y squared equals z. This is in rectangular coordinates. What did that look like? Well, we have different things. If z equals 0, what do we got? We have the origin, right? So we got x squared plus y squared equals 0. So that's the origin. And what if z equals, let's say z equals 4? Well, that's x squared plus y squared equals 2 squared when z equals 4, right? And what's that look like? Let's see. So when z equals 4, up here, I have a circle with radius 2. So I'm out 2, left 2, back 2, etc. Got the origin here. What if z equals -4? That doesn't work, right? If z equals -4, you can't have x squared plus y squared. By the way, this was 4, right? Because z equals 4. X squared plus y squared equals -4. That doesn't work. So we can't have negative values. And what happens as z gets bigger, like if z equals 9, then we got x squared plus y squared equals 9, which is 3 squared. So that is a bigger circle. So this was when z equals 4. Up here at z equals 9, we got a bigger circle. And we have this type of deal here. Whoops, I was supposed to touch here. But anyway, that is a circular paraboloid, if you remember that. So the good news is, since you got a review for a final exam anyway, then this is good stuff that we did back then. Of course, it keeps going out and up forever with bigger circles as we go higher. The other thing that we could look at is, before I look at this in cylindrical, is when we were graphing this. Let's just use a different color here. But if I solve this for well, let's see. If I guess let's let x, if x equals 2, what do we have? Then we got 2 squared plus y squared equals z. And so this is y squared plus 4 equals z for the particular x equals 2. And what do we have? That ends up being a parabola, right? For that. So anyway, this is a circular paraboloid, I believe is what it's called. But anyway, how the question is not try to rehash and go back over what we already did in 10.6 and chapter 9, but what if we wanted to rewrite this using using rectangular coordinate, cylindrical coordinates? What would it look like? Okay, well, z equals z, right? So that part doesn't change in cylindrical, but the question is, what would it look like over here? So let me clear this. Remember that equation for me, and then go back there. But here's what we have. We have, for cylindrical coordinates, r cosine theta and y equals r sine theta. So this is just from geometry. When I'm drawing the cylindrical coordinates and I've got this point here, once again I come down here, this is r right there, and this is theta, right? So the question is, how do I get my x? My x would be, what is this? This is my x value right here, but this is the adjacent. So the adjacent side divided by the hypotenuse is the cosine. So the cosine of angle theta right here, cosine of theta is the adjacent side, which is x divided by the hypotenuse r. So we just solve both sides and we get that x equals r cosine theta. Very similarly, we can do that for the y value as well, because if this is the y value right here, then this theta angle right there is the same as this one right here, and that's opposite over hypotenuse, and that's sine. So the sine of this same angle theta would be y over r, which means that y equals r sine theta. So we have this equations representing cylindrical coordinates from graphical. Of course, we also had z equals z. Z didn't change, right? And then what else could we do? Could we square both of these equations? And if I do and add them together, I'd get x squared plus y squared. What's it equal? It equals r squared cosine squared theta plus r squared sine squared theta, which is factor out an r squared, and we know that sine squared plus cosine squared is 1. So we also have that r squared equals x squared plus y squared. And we can also say that, hey, tangent of theta over here, so the tangent of this theta is opposite over adjacent. Well, the opposite of theta is y, and the adjacent angle to theta, or adjacent side, I mean, to theta is x. And of course, this is true as long as x doesn't equal 0. Okay. So if x doesn't equal 0, we also know that the tangent of theta is y over x. So we have all of these representations in cylindrical, which we were just getting to that yesterday. And so let's go back, as long as it lets me keep writing here. Let's go back to our equation. We had x squared plus y squared equals r equals z, sorry. And we had this in rectangular coordinates, and it was the circular parabola, paraboloid, right? Circular paraboloid, sitting on the origin and coming around, like that. So what would this look like in cylindrical coordinates? Well, we know that x squared plus y squared is r squared. So r squared equals z has the same exact graph sitting on the origin, okay? Where the x-axis, the z-axis is right there, right through the middle, the y-axis and the x-axis coming out, right? So we have that same exact graph, but this would be in cylindrical coordinates. Okay, so once again, is that any easier? Not necessarily, but some are easier, some are not. So they do want you going back and forth on some of these to come up with different things. All right, so let me clear that off and see what else we need. Let's see. What if we had, let's look at an example, possibly. What if I have R equals 6 sine theta. What's that? Question is, if I wanted to rewrite that, so this is in cylindrical, and if I say, hey, I want to rewrite this in rectangular, how would that go? Well, if we have R equals 6 sine theta, okay, we got to use those equations I just had up here. Well, I don't have just an R. I have X equals R sine theta, but I don't have anything for 6 sine theta, things like that. So, you know, how in the world can we make this look like rectangular? So that's the question. We want rectangular, see what that looks like. Well, one thing I could do to both sides of an equation is multiply both sides by r. And if I do that, I'm going to get r squared equals, multiplying the right side by r is 6r sine theta, right? Now, what I can do is, once I get the lights back on over here, is I can take this r sine theta and rewrite that, because I know that that is y, right? So this is, instead of 6 times r sine theta, this is 6 times y. And instead of r squared, I also know that that is x squared plus y squared. So I could rewrite this equation in rectangular coordinates as x squared plus y squared equals 6y. So that's part of how we can go back and forth and determine, you know, which ones we want, etc. Anyway, and I'm not gonna try and graph this one. So the book does have some examples of different graphs, different shapes, things of that nature too. But let's look at one more possibly, and then move on to spherical coordinates. So I've got, let's see. Let's if I have r times 3 cosine theta plus 2 sine theta plus 6z equals 0. How could I rewrite that? That's in spherical coordinates, right? Because it's got r, theta, and z. And so this should be fairly easy. We can just multiply that r through there, right? And I have 3r cosine theta plus 2r sine theta, 2r sine theta plus 6z equals 0. And of course, I can replace the r cosine theta with x, and I can replace the r sine theta with y, so that's an r in there. But anyway, so plus 2y plus 6z equals 0, which I believe that is a plane with a perpendicular normal vector of 3, 2, 6, if I remember the equations right. So I'll let you go back and verify that. But anyway, that should be a plane through space with perpendicular normal vector, one of them being 3, 2, 6. Okay, and actually I said I didn't want to graph the last one, but I am going to go back. I think we should. So what did we say? We said r equals 6 sine theta, and what's that graph look like? Well, if we were rewriting it as x squared plus y squared equals 6y, then what I could do is get the 6y on both sides. So x squared plus y squared minus 6y equals 0. I could complete the square here, right? So how do I do that? Half that coefficient quantity squared, half of that's -3, quantity squared is plus 9. So I can rewrite that as plus 9 on the left side, but if I do that on the left, I got to do it on the right. And then how could I rewrite this part? I could rewrite it as whatever half that coefficient was minus 3, so it's y minus 3 quantity squared equals 9, which is actually 3 squared. So this is an equation of a circle, but the difference is the center. This is a circle centered at where you plug in to get 0. So the center is actually x equals 0 and y equals 3. Okay, so if I was going to graph that in 3 space, so x is 0, y is 3, 1, 2, 3. This is the center. The radius is 3. So I'm getting, anyway, so 0 to 3, that's one of the radius. This is the other radius. And then I go back 3 and out 3. And then so really what I have here is a circle. That's when z equals 0, but z is unrestricted, isn't it? So for both of these, z is unrestricted. And so really what we have is we have a right circular cylinder again with radius 3, but it is centered. My center isn't very good. I'm just going to draw a vertical dashed line. My center right in the middle of that is when x is 0 and y equals 3. And then it goes around that black virtual center up and down was the unrestricted. Okay, so that kind of tells us, hey, r equals 6 sine theta. You know, we can draw that pretty quickly, represent that pretty quickly with a right circular cylinder that is really up on the, or out on the positive y-axis. Okay. Everybody think, hopefully you're all good on the cylindrical coordinates for now until you get into something that maybe is a little bit awkward. You can reach out, okay, through our communication tools. All right, so let's go into spherical coordinates. Spherical. Okay, so spherical coordinates are a little bit different. So when I have my 3 space out here, once again, I got my x out, y over z up. And if I want to represent a point in space right here, I'm going to do this a couple of different ways. So let me use a different color here. This is on page 1071. But this is going to be, let's see, the distance here from the origin, this distance here, they call this Greek letter, which is rho. Okay, so it looks like a funny looking P. Anyway, so that's spherical. So that's rho. And then of course, if I drop this down, I'm going to go back to black. If I drop this down in the plane, you know, and the reality is I'm coming out here. We still have an angle theta, right? We still have an angle theta to get here. Because this is basically out in octant 1, it's kind of slicing out, but rho is going to be this distance there from the origin to that point, where that point in space before in rectangular is x, y, z, right? But anyway, so I have a distance of rho from the origin of that. I have an angle theta to get over there, but the difference is I need another angle. So I'm going to take an angle off of the z-axis to come out into octant 1 and get there, and they're going to call that angle phi. So it's a circle with a slash, kind of like an empty set notation. And so in spherical coordinates, what's this going to be? This is rectangular, but in spherical coordinates, let me go back to green. We're going to call this point rho, which is the distance from the origin, theta, which is the angle from the positive x-axis toward the y-axis, and then phi, which is the angle from the positive z-axis toward the table surface, so to speak. And then, of course, what do we want with phi? We want phi to be between 0 and pi. You know, so basically it's going to come all the way down to the bottom side of this axis, and then of course depending on if you're around farther on the backside or whatever, but phi can go all the way, you know, from 0 to pi, or coming out octant 1 all the way down to pi. So it really doesn't need to be anything but in here. And then you know, theta is basically the same as before, so theta is going to be between 0 and 2 pi. But do notice if phi here is pi, let's say that, let me use a different color. If phi equals pi, where are we at? Phi equals pi is going to go all the way down here. We're on the negative z axis is where we're at. So negative z axis. So hopefully that makes sense on there. And then how would I know if I'm on the positive side of the z-axis? What if I'm up here? What would that mean? That would mean that phi equals 0. Perfect. Okay. So what do we know on a couple of things? So let's look at an example in spherical coordinates. What if I have rho equals a constant? So if rho equals, let's say rho equals 2. Well, what does that mean? So let's kind of draw that out. Here you got your x, y, z, 3 space, but rho is my distance from where? From the origin, right? So if rho is a constant, what's unrestricted? So we have the next two variables, theta, so the angle around the table surface is unrestricted, and so is phi, which is the angle from the z-axis coming down. So that could actually just keep going all the way around too. So all we know, these are unrestricted, but my distance away is 2. So whether I'm over 2 to the right, or I'm out 2 on the screen, or I'm up 2, or I'm down 2, 1, 2, right? Or I'm back 2. Well, what does this make? If I let x be 0, I have a vertical circle, right, in the the YZ plane. If I let y be 0, I have a vertical, a circle coming out of the board that goes down and then back. And of course, if I let z be 0, then what do I have? I've got a circle coming out, back there. So what does that make? That ends up making a sphere with radius 2, centered on the origin, right? Sphere with radius 2, centered on the origin. So the center is on 0, 0, 0. Okay, or the origin. So since this is the first variable, because remember in spherical coordinates we have rho, theta, phi, then what do we know? Since rho is a constant, it looks like a sphere. What do they call these? They call these spherical coordinates. Just like the first one, r equaling a constant before, looks like a cylinder, right, circular cylinder. So they call them cylindrical coordinates. So that's how you can remember how they name them, different things. So let's look at, see if we can do a couple other quick action items here. What if we have theta equals a constant? So let's just pick one. Let's look at theta equals pi over 4. So what's unrestricted? We have example that we're doing is going to be phi equals a constant, and I said let phi equal pi over 3. Okay. So coming back to this one, theta, once again, this is no different than before. I use a different color, staying black up here. Theta is coming off the x-axis and toward the y-axis. So pi over 4 is, I'll just do this one in red here. But anyway, pi over 4 is a split in this, right? And then, of course, my distance away at any point is unrestricted, and my angle down from the z-axis, so we have rho and phi are unrestricted. Then basically what we end up getting is a plane. Okay, now what did we say for phi? Phi goes, so my red is supposed to be perpendicular or parallel to this thing here, but phi can come down here, and so we have this half plane. But if we don't want phi to be go past pi radians, then I'm not getting the back side of this. I'm only getting the front side that comes down from quadrant 1 as a, or octant 1 as a vertical plane. Okay, so that's what we have there. And then the next one, when we have phi equals pi over 3. So let me put my axes in here, x, y, z axis there. But for phi, once again, phi is the angle down is pi over 3, but what's unrestricted? So we have rho is unrestricted, distance away, and theta. So theta, once again, that's that twister spin, can go all the way around, but we're always going to be coming down at an angle of pi over 3 from the vertical z-axis, which pi over 3 is 180 divided by 3 is 60 degrees, right? So anyway, so we're coming down this way, but you know, rho is unrestricted, so I can be as far out as I want here, and then you know, I could come out the other way, or you know, other ways. But long story short, I can come around like this, and all of these look like a cone. I think that's what that's called, right? So a cone sitting on the origin. Okay, and what happens if phi happens to be bigger than pi over 2? So let me just let's say, what if phi equaled 2 pi over 3? Well, then I'm down 180 degrees, and I'm going to be, so my phi would go down. So basically I'm below that surface here. I'm underneath the table surface for the XY plane, right there. So if phi was an angle between pi over 2 and pi, it's going to be down below the table surface. If it's 0 to pi over 2 for phi, I'm going to be above the table surface with my cone. So hopefully that makes sense for you. All right, and I'm kind of running, I'm sure I'm running you thin on your stuff. So let's look at a couple of quick identities that we have in this section for spherical. So for spherical equations, what do we know? We have x is going to equal rho sine phi cosine theta. And we're going to have y is going to equal rho sine phi sine theta. And we're going to have z equals rho cosine phi. Okay, so I think the best way to remember this is, hey, we've got rho sine phi for x and y, and for x I'm going to attach that cosine theta, just like I had r doing that, x equaled r cosine theta before, and I'm going to attach the sine theta on the y. So if you remember back in cylindrical, what did we say? We had x equals r cosine theta, and we had y equals r sine theta, right? So anyway, that might help you remember that. And then in this case, then we got z equals rho cosine theta. If you squared both of these out, if I took x squared plus y squared, okay, and then plus z squared, if you squared all three of these out, added them all together, you're going to find out that it ends up equaling rho squared. So this is a really nice equation that we have as well in spherical coordinates. So they do go through the details of that on the middle of page 1072. So instead of me going through all that stuff, I've kept you long enough today.